There's a remarkably straightforward method to reduce your home's temperature by as much as 25 degrees Fahrenheit for the minimal expense of a few earthenware pots and a gentle water flow. This cooling approach surpasses contemporary air conditioning systems in extreme heat, consumes 80% less energy, and operates without chemical coolants, compressors, or intricate electronic components. Nevertheless, while the $100 billion HVAC industry markets plastic contraptions that cost thousands to install and hundreds monthly to operate, this effective technology remains largely unknown to the majority. So, what exactly is this system? How does it function? And, more critically, why aren't we all implementing it? Let's investigate. To truly appreciate the genius of this technique, we must journey back to the parched, scorching plateaus of ancient Persia and the sun-drenched courtyards of Egypt. Millennia ago, survival in these landscapes was not a matter of comfort but of fundamental biological necessity. The architects of that era confronted a profound challenge: how to maintain a habitable environment in a city where the external temperature frequently soared above 113 degrees Fahrenheit. Their ingenious solution was not a machine, but a material. They observed that unglazed, porous earthenware vessels, when filled with water and positioned in the path of a prevailing breeze, possessed the remarkable ability to cool the surrounding air. This profound insight gave rise to the mashrabiya in the Middle East and the jali in India, ornate perforated screens that harnessed the inherent properties of earth and wind to cool entire palaces long before the advent of electricity. By 400 years before Christ, the Persians had elevated this principle into the yakhchal, immense domes constructed from mud brick that stretched 59 feet into the sky. These structures served as sophisticated natural refrigerators, employing subterranean reservoirs and wind-catching towers to produce and preserve ice even during the peak of a desert summer. This technology eventually found its way to the Indian subcontinent, where it was embraced and further developed by the Mughal emperors. During the 16th and 17th centuries, the Mughals engineered the Abdar Khana, or water house, and the Baraf Khana, the ice house. These were not merely storage facilities, but active thermal systems utilizing sandstone cisterns and insulated cellars. Emperor Akbar famously orchestrated an elaborate relay system to transport ice from the Himalayas to the plains of Delhi. However, it was the domestic production methods, utilizing shallow ice pans and straw-lined pits, that truly demonstrated the efficacy of terracotta and earth in regulating temperature. These historical precedents firmly establish that cooling with mud and water is neither a novel nor an alternative innovation. It represents the reawakening of a resilient technological heritage that was systematically sidelined by the 20th century introduction of chemical refrigerants. The contemporary resurgence of this forgotten knowledge occurred in 2017 with the creation of the beehive terracotta cooler. Siraparapu, an architect based in New Delhi, encountered a critical issue at a local electronics factory, where the heat generated by a massive generator created a 50-degree heat island effect that conventional air conditioning struggled to counteract. He recognized that the ancient geometry of the beehive, a form that maximizes surface area within the most compact volume, could be combined with traditional pottery techniques to address this modern industrial problem. The beehive cooler functions based on a fundamental principle of physics. When water evaporates, it absorbs heat to transition from a liquid to a gaseous state. In this system, this heat is directly extracted from the air, a process known as evaporative cooling. To comprehend how this occurs, one must examine the clay itself. Unglazed terracotta is a porous material, riddled with millions of microscopic channels. When the structure is moistened, these channels act as a network of minuscule conduits, drawing water from the reservoir and distributing it throughout the clay body, ensuring that every exterior surface remains saturated. This phenomenon, known as capillary action, guarantees a continuous, uniform film of moisture on the cooler's surface. The beehive's geometric design is what elevates this from a simple damp vessel to a high-performance cooling apparatus. If one were to employ a flat, wet surface, the air would simply glide over it with minimal heat loss. However, by assembling hundreds of terracotta tubes into a honeycomb configuration, an enormous surface area is created within a confined space. As the hot exterior air is drawn into these tubes, their circular form imparts a tight spinning motion. This turbulence ensures that every air molecule makes contact with the moist clay walls. Upon impact, the water on the clay's surface absorbs the thermal energy from the air to facilitate its own evaporation. Furthermore, this design ingeniously leverages another physical phenomenon, the Venturi effect. As the air is forced through narrower passages, its velocity increases. This accelerated airflow causes the water to evaporate at a significantly faster rate, which in turn further reduces the air's temperature. By the time the air exits the stack, it has been stripped of its heat and enters the interior as a dense, chilled current, potentially up to 27 degrees Fahrenheit cooler than the external environment. In the aforementioned electronics factory in Noida, this arrangement of clay achieved what conventional mechanical cooling could not. It lowered the temperature from a scorching 122 degrees Fahrenheit to a manageable 97 degrees Fahrenheit. However, the system's success is not solely measured by temperature reduction. Unlike standard air conditioners, which dehumidify the air and can leave occupants feeling dry, the beehive cooler purifies the air while introducing a natural, gentle humidity. This process generates petrichor, the distinct earthy aroma released when rain falls on dry soil. This is not merely a pleasant, incidental outcome, it has a documented psychological effect on the human brain. When we perceive the scent of petrichor, our sensation of heat diminishes more significantly than objective temperature readings might suggest, providing a profound sense of relief that a plastic, chemically based unit cannot replicate. The energy data collected from the Noida project underscored the remarkable efficiency of this system. To cool an industrial space of comparable size, a conventional mechanical air conditioning system would have consumed substantial amounts of electricity. The beehive system, conversely, accomplished the same task with a measured 80% reduction in energy usage. The entire installation operated on less than 0.63 units of energy per hour, providing industrial-grade cooling for less than the cost of running a few household light bulbs. In an era of escalating energy prices and an unreliable electrical grid, this project demonstrated that modern comfort is attainable without resorting to the expensive grid-dependent systems we have been led to believe are indispensable. But if this technology is so effective, why isn't it the standard for every residence in the United States? The most apparent reason is that it is not a viable solution for many homes situated in inappropriate climates. Evaporative cooling is considerably less effective in humid environments because the high ambient moisture content impedes water evaporation. Similarly, in regions experiencing extreme temperature fluctuations between summer and winter, a permanent open structure like this would necessitate highly sophisticated designs to mitigate heat loss during colder periods. In such locales, mechanical heating systems represent a logical choice. However, numerous residences within the Sun Belt could benefit significantly from the beehive structure as a potent passive cooling mechanism. For these homes, the primary obstacle is not climatic unsuitability, but rather the inherent structure of our economy. The global cooling market is dominated by a few colossal corporations that depend on a revenue model of high-margin sales and planned obsolescence. An air conditioning unit is a complex apparatus with numerous moving parts, engineered for annual servicing and complete replacement every 10 to 15 years. A stack of clay pots capable of lasting for half a century offers no such recurring revenue stream. One cannot market a technology that individuals can construct themselves using readily available earth. Consequently, the industry simply ignores it. Furthermore, in the United States, this system faces significant hurdles due to our stringent building codes. For the past 50 years, American homes have been designed as hermetically sealed, plastic-encased structures. Our regulations are predicated on the sealed envelope model, which mandates mechanical ventilation to ensure breathable air quality. The beehive cooler, in contrast, is a naturally ventilating system that requires constant air exchange with the external environment to function effectively. Because it does not align with the standardized efficiency ratings employed by building inspectors, it is frequently legally prohibited from primary residences even before construction commences. Developers and property owners also exhibit limited interest in such solutions, often opting for the most cost-effective cooling system to install, the standard electric AC unit, as they are not the ones bearing the monthly utility expenses. The tenant incurs the cost of electricity while the landlord avoids the complexity of integrating a more efficient, unconventional system like the beehive. We find ourselves reliant on technology that is expensive to operate and detrimental to the environment, not because it represents the optimal solution, but because it is the most profitable or convenient for those who construct or sell our homes. However, you can embrace this technology today without awaiting a commercial product to appear in your local retail establishment. Because the underlying physics of the beehive cooler are open source, the barrier to entry is remarkably low. If you aspire to build a functional unit this weekend, The most accessible approach is the flower pot method. You will need to source unglazed terracotta, either in the form of pipes or standard garden pots. The unglazed characteristic is paramount. If the clay is fired with a decorative glaze, the microscopic pores become sealed, preventing water from migrating to the surface and facilitating cooling. To assemble your structure, arrange these pots in a honeycomb configuration within a simple wooden or metal frame. This arrangement ensures that as air is drawn through the central openings, it is compressed and compelled to interact with the moist clay. To automate the system, place a small 12-volt fountain pump in a reservoir at the base and connect a plastic manifold to the top. This pump will gently trickle water over the stack, maintaining the clay's saturation. By connecting this pump to a small 20-watt solar panel, you create a self-regulating mechanism. As the sun's intensity increases, the pump operates more vigorously, enhancing cooling precisely when it is most needed. For those seeking a more sophisticated or industrial-scale installation, Ant Studio in New Delhi, under the leadership of Monish Sirapurapu, offers specialized design services. They have evolved the beehive concept from a single factory experiment into a modular system that can be seamlessly integrated into the facades of large buildings. Although based in India, their work has inspired a global network of architects and designers who are adapting these terracotta modules for diverse climatic conditions. If you are interested in hands-on training to master the integration of these systems into sustainable architecture, organizations such as the Center for Science and Environment in India, along with various permaculture institutes in the United States and Europe, provide workshops on passive cooling and traditional building techniques. The beehive cooler represents a 4,000-year-old answer to a contemporary challenge, illustrating that we need not be tethered to the power grid to maintain comfort in a warming world. By harnessing the way water moves through porous clay to absorb heat, we can cool a home for the cost of a few garden pots and a small solar pump. Many of the solutions we discuss on this channel have been marginalized due to insufficient profitability for commercial sale. If you find this type of knowledge valuable, subscribing and sharing is the most effective way to ensure its preservation. And if you wish to discover how this same principle of evaporative cooling led to the creation of an off-grid refrigerator that benefited thousands of Nigerians, that video is available next.